Good afternoon, and thank you for joining this webinar. Again, I'm Jared Hansen. I am the lead electromagnetic specialist for RAND simulation. And today we're going to talk about enhancing your electronic designs using Ansys tools. A little bit of the agenda for today as we're moving forward. Hopefully, there we go. This is really an overview webinar of the Ansys tools. The goal here specifically is to talk about the tools and then throughout the 2020 year, really go into specific workflows within individual tools. So we're going to, talk about low frequency, we're going to talk about high frequency, we're going to talk about thermal analysis within the electronics desktop and tools for that can be used for your electronic design. Really as a high level overview, Ansys has a lot of different electronic tools within their enterprise solutions. And really these tools provide a full system for electronic design, full system solutions within electronic design rather. The goal of this, is to take engineers and get them away from the workbench where they're now trying to figure out where their problems are coming from and let them simulate their components, their electronic systems prior to fabrication to save time, effort, money, and sometimes sanity. This is what's really interesting about the the Ansys electronic tools is it's not just an antenna design tool. It's not just a signal integrity tool. It is really a full suite of tools to solve your system. And just to take a little bit of a step back, why do we simulate? I kind of talked about it briefly, but it's to build confidence in our designs. It's to reduce or mitigate risk. It's to get your product to market faster with confidence and make better decisions. Now, within this tool set, there are things that can be used for on the 3D level, on the circuit level, and we'll talk about all of those today. But, there are a lot of simulation tools out there. And the real question is, why Ansys? Why spend the money? Why spend the time learning it? And at the end of the day, the answer that I always give is accuracy. You want to simulate, and you want to use a simulation tool that you can trust and that you can make sure is accurate. And the way that we justify the accuracy is through for 3D level for the use of adaptive meshing. And what I'm going to show you right now is a patch antenna and the process of adaptive meshing and the result of the return loss or S11 on that patch. So as you can see, it starts out very rough and refines that mesh. Now this is, as you see both on the mesh and on the accuracy on the right for the S11, the initial one was very far off from the what would be expected or realistic performance. And through the refinement of the mesh, you can see that the accuracy of that S11 increases as each adaptive pass moves forward. So this really is what I think makes Ansys, especially HFSS and Maxwell unique, are these adaptive meshing tools. This is one where an engineer doesn't need to go in and define a mesh. The tools will generate the mesh for you with the respective frequencies of interest. So with that being said, move forward here. Here's really the overview of the EBU products, and that being the electronics business units. So the HFSS being your high frequency tool, which is your 3D, so antenna design, 3D board layouts, signal and power integrity, and we'll get into more detail on all these, but these right here, so HFSS, Maxwell, SI Wave for PCB analysis, Icepak for thermal analysis, Q3D to look at parasitics, and then finally the electronics desktop, which is really the GUI where all of these solvers are housed. So we're going to go through in some detail, some general detail, each of these tools today. Now I'm going to start in the low frequency end. The low frequency tool for Ansys is called Maxwell, and this is really what I consider the gold standard for motor, transformer, sensors, permanent magnets, and all that simulation in those areas. And within Maxwell, there are a host of different solvers that you can use to aid your design and find solutions. These range from the static DCs, transient analysis, as well as eddy current and AC analysis. The other thing that's interesting is not only are these field solvers, 3D field solvers, but you can also use and include circuit and system simulation with your models. So now you get the benefit of not only having the 3D solver, but you have the schematic, the lump parameter models as well. In addition, Maxwell has a 2D solver, which you can use to not only save on runtime, you can decrease complexity to speed up your processes as you're developing these low frequency tools. And within Maxwell, you don't just have to bring CAD models or create geometry within the 2D or 3D solver. You can use tools such as PExprt, which is a template-based design tool. This will allow you to build your rotating machines on the template base and then build them from that template into a 2D or 3D model where Maxwell is now creating the geometry from the specifications that you have here in these templates. In addition, not only do we have this for rotating machines, but we also have PExprt, which is specifically for the design of power electronics, so inductors and transformers, where you can now set values, set material properties on this, using this analytical tool, and then building a 2D and 3D model from this. And just like you would expect to see in Maxwell for looking at things like core loss, flux density, eddy current effects, those kind of results, you'll also be able to see those kind of measurements done using this analytical tool. In addition, you can, like I said before, it's not only the 3D or 2D model, but you can generate reduced order models for the Simplorer tool, for the circuit tool. So I've talked a little bit about, low frequency, and I look forward to going into more depth in the future about the low frequency tools. But at this time, I'm going to move into some high frequency. So if there's any questions pertaining to low frequency tools, I'd love to answer. It's tough to see if there's any because I'm sharing my screen. But if there are any, don't hesitate to ask in the Q&A box. If not, I can move on. Okay.
Jared, I don't see any questions right now, so you can.
Okay. So moving forward, again, so why use Ansys for high frequency simulation? Ansys tools are for high frequency, or they're finite element array, Mona method, or asymptotic approximation based. These are all used to calculate the electromagnetic field. And this is really an advantage of these types of solvers, because we get to look at physical, the physical the physical properties of our geometry, where a traditional circuit or lump parameter model doesn't get that effect. Lump parameter models are really good and really effective at lower frequencies. But as you get into these high frequencies, these gigahertz, these terahertz range, they really begin to break down. And having a field solver simulation tool is extremely important. And while HFSS, while these other tools are high frequency, they are field solving tools, the electronics desktop also includes a circuit solver for linear and nonlinear circuit simulation, which can then be used and included with your 3D geometry to get a full system solution for your designs. The tool that I'm going to talk about, and I'll probably talk about the most, is HFSS. Especially for high frequency, this is the gold standard for high frequency simulation. There are a host of different things that you can do within HFSS. The solvers within HFSS include things not only just frequency domain, but also time domain. And what's interesting about HFSS and the solvers within it is it's not just a field, it's not just an FEA solver. It's not just a full wave solver. We can talk about, on the low level, there is the full wave, which, this is a great tool for, simulating things like antennas, arrays, and the common antennas that we see today. But as we get larger, electrically larger, we don't have the time to solve problems that we have and that we see on a day-to-day basis. And so within HFSS, there's also hybrid solvers for including electrically larger geometries. And here's we talk about tens of wavelengths, hundreds of wavelengths, and then eventually within the tools, we get into the thousands of wavelengths away. And in a typical full wave solver, we're talking about an extremely long time to get to these thousands of wavelengths solved in a traditional method. But with the SBR tool, which we'll talk about in just a second here, you can solve these problems, these radar problems, in a way quicker, in an as accurate simulation tool. So within HFSS, there's a tool called SBR Plus, where SBR stands for Shooting Bouncing Rays. This tool allows you to take an antenna that is simulated in a full wave simulation, take those results, and apply it to an electrically large simulation. So the depiction on the right, of course, is that of an airplane, a great electrically large problem. And it's not just one antenna on the airplane; it could be multiple. And with this tool, and starting out small with a full wave, where we're now again talking about tens of wavelengths, you can simulate these antennas and then bring them in to this large model and get the results that you see below. And this is I see that they included the simulation time for a model that is very, very large. Included in SBR Plus, things like radar cross-section analysis, creeping wave, and some other applications that are interesting for electrically large problems. Within, so we talk about different solvers, different applications. Within HFSS, there is something called the RF option. And this is really the focus now on microwave and microwave circuits. So when we talk now not only about the antennas that are being developed, but also the circuitry that is just as important, we need to now look at a not only linear but nonlinear circuit development. And you can do this all within HFSS and the electronics desktop. So this is an interesting addition to an HFSS tool because, again, we go back to HFSS is not just Ansys electronics desktop is not just an antenna designer. It's a system solution tool set. And so this is one of those where you can design the antenna in HFSS, you can design the circuitry within the electronics desktop, and get that system solution for your microwave electronics. In addition, there are other options that can be included. The next one is for signal integrity. So this is the SI option within HFSS. This option is now where if you're interested in bringing in your PCBs into HFSS for analysis, you can go in and simulate things such as eye diagrams, transient analysis for your models, and you can include things such as IBIS models to increase the strength of your simulation. There is a nice EMI toolbox that goes through and gives you some predictive rules for where you may be seeing EMI issues. And this is all done within the HFSS. This is now 3D layout, but this is where you can bring in your PCB and then analyze it before you manufacture for signal integrity. So just a little transition now from signal integrity now into a tool that's used specifically for EMI issues is the tool called emit. And so the next slide. So this is a tool that you can include where you can analyze and investigate your EMI issues in the pictures we show. Co-site could be potential co-site issues due to multiple antennas. It can be desync due to having high-speed lines and an antenna on a PCB. And really what's interesting about emit is it allows you to look at the root cause of where the problems are coming from, whether it be in this 3D geometry or trace level on a PCB, and you can quickly analyze your PCB or your 3D geometry and move, or in the case of geometry, via fence or add other techniques to solve your EMI issues. A little bit related, so I'm going to take I'm going to pivot a little bit here, and instead of talking about HFSS and all of the tools within HFSS, I'm now going to move to SI Wave. SI Wave is the signal and power integrity, also DC analysis, specifically for PCBs. And this, so if I quickly jump here, SI Wave is an interesting tool because it is now, and it was made specifically to analyze your PCBs. This includes things like IR drop for DC, and then from IR drop, we can incorporate or couple with other physics to look at thermal analysis. This includes an ECAD import, so you can bring in your ECAD from tools like Altium, Mentor, and a host of other tools. And this is, again, this is a really unique tool because it's looking at signal and power integrity, and it has a lot of toolkits within it to help develop and design and diagnose problems on your PCB. I've worked with some clients and customers where they're interested in EMI. I think probably a lot of people, they'll say their board has EMI issues, and that is, the end problem, right? We don't know the cause of that EMI, and so having a tool like SI Wave, you can go in and diagnose: is it signal integrity issue? Is there current issues? Do I need to add decoupling capacitors? Do I need to look at impedance of my traces? This is all within the tool that you can then analyze your PCBs and make these corrections. Bring it back, take it back to your designer, your Altium, make the changes, and you can then bring it back into SI Wave, see if those changes were effective, and then you can fabricate from there. So again, you've removed the step of creating your PCBs, fabricating them, and then testing on the first revision before having any knowledge of how your PCB may function. So now you can design, you can simulate, you get those results, you can fabricate. You have a fair amount of confidence going into that testing, so you can have a better idea of how your device is going to work, and really building confidence going into testing such as FCC, things like radiative immunity. It's something that everyone, we all have to go through, and getting stuck there and having to redesign due to a failure is costly. It's time consuming, and it is if you're not simulating your designs, at times you're praying and hoping for the best. Within SI Wave, there are 3 different levels. The first one is the DC SI Wave. This is your, just as it is, this is your DC analysis. So your IR drop, which you can then, as I said before, couple with thermal, look at return paths. This also, you can get, not just as important as getting A-links. This is your ECAD translation tool. So from, Altium, from Cadence, you can quickly import those boards into SI Wave. Going from there, there's SI Wave PI, and that includes, all of those things listed there. I've seen a lot of use with the SYZ analysis as well as the decoupling optimization, and I look forward to going through a workflow on both of those because they're just exciting to show off. So when we talk, decoupling is not only value but position, and you can simulate rapidly where to place decoupling capacitors on your PCB and the effects that they have on your SYZ characteristics. And then finally, there is SI Wave, which includes all of the tools as well as the near-far field and the incorporation of IBIS models and transient solves. This is again increasing strength with the tools, and some I don't have listed here that incorporates IBIS models is looking at DDR X, looking at DDR for compliance. So we design, we have what is given to us by the manufacturer for information related to DDR, and we want to ensure that it is meeting the specifications. Our PCB is meeting the specifications set up by the manufacturers. This tool, SI Wave, has a very nice workflow for generating the criteria for basically all the DDRs. And it is, although it can be time consuming, the results are very impactful, which I've had a chance to use it multiple times now, and it's another one that walking through that workflow, I'd love to do and show you how you can analyze those, that information. Included in all this, obviously, analyzing high speed. So looking at your USBs, looking at that kind of information with things like eye diagrams, You can generate that information from SI wave, and you can incorporate. What's also interesting is you can take SI wave, you can do a PCB or a trace level solution there. If you have a connector, you can then incorporate it with HFSS and then solve for the connector and the trace level within HFSS, looking at S parameters, for example. And this is a pretty common workflow, but this is one now where you'll have a good understanding of not only how your connector works, but also how your traces are impacted by that connector. I'm gonna take a drink real quick. I'm sorry. I move on from SI wave. Are there any questions on either HFSS or SI wave or any of the tools we talked about so far?
I haven't seen any come through.
Okay. Am I catching like the lunch? You know, I know it's 12 o'clock in Central, so Central time. So probably a lot of people eating as we go about. The next thing I'm gonna talk about, I'm gonna take a step back from SI wave and talk about Q3D Extractor. This is a nice addition to the tool set where this extracts parameters for traces, connectors, and a host of other components. This is one where it functions and works well with, of course, HFSS, but it is a nice addition to a lot of different tools. Again, including the IBIS package. This is where you can create and model circuitry for your traces, as well as things like touch panels, by including field coupling, and a great host of other tools. I think this is can be an underutilized tool within Ansys, and I think there's a lot of strength behind it in how you can model things that you couldn't before using HFSS or SI wave, and there's a lot of strength with this tool. And I'm probably not giving it enough time to really talk about how great it is. I'm going to jump into Icepak right away. Icepak is the electronics cooling tool. This is a tool that uses the Fluent solver, but it's built and integrates a lot of the electronics workflow. And what I mean by that is the creation and simulation of electronic models for thermal solutions very rapidly. You know, and this includes things like a library for a host of different fans, common heat sinks, you know, and a lot of different tools that you can include. And of course, because it uses Fluent, things like conduction, convection, and radiant heat are all able to be modeled. What's interesting is now, not only is there Icepak Classic, but there's also Icepak that's integrated within the electronics desktop. And I'm going to talk about that a little bit later. But you can also import not only MCAD geometry, so step files, but you can also import ECAD geometry, so PCBs, and you can analyze thermal characteristics with not only now your step geometry, your MCAD geometry, but also your ECAD trace level, and below that even for thermal analysis. This tool, and I've been using it more and more. Icepak Classic is a great tool to include with your simulations, because after you've developed, whether it be low frequency or high frequency, when you've developed your electronics, you want to ensure that their behavior thermally is not going to damage either themselves or something else. And this is a great tool for that. The workflow from a step file to bring it into Icepak Classic is very streamlined. You can do it through SpaceClaim, or you can bring it into the electronics desktop, and you can do your analysis within the electronics desktop. So there are multiple ways to use the tool. So if you have a mechanical engineer that is interested in simulating thermal and is more comfortable with a certain GUI, you can have the workflow of using Icepak Classic. Or if you have someone that has used the electronics desktop, you can have them bring the geometry into the electronics desktop using Icepak, and then you can solve within Icepak and the electronics desktop. This is within Icepak. It's not just, the image showing here is a system, but you can get all the way down to trace level, to pad level, and simulate from there. Multi-layer boards, the properties within those, so importing ECAD geometry in, the thickness of your boards all get brought in as well in a very streamlined method. And again, what's really great about this tool is you bring in this, and you have electrical engineers working with this thermal tool, but you get the strength of Ansys and the accuracy of Fluent, of using a CFD tool for your thermal and flow. And so, just a quick step to look at, again, this is bringing Icepak into the electronics desktop, just like you would open up an HFSS, a Maxwell, or a Q3D project. So for anyone here that's already using the Ansys tools, you can see that I have created the project here, and you can, for someone that's already comfortable using the tools, this is a great addition. And just like with the Icepak Classic, you have the Icepak components, fans, heat sinks, etc., all here for you. And so, again, this is an example of a system, but it's the inclusion of not only a heat sink, fans, PCBs, but also the component level. And if you want to, you can increase the fidelity for layers, traces, vias, and that level that you may be interested in looking at and trying to better understand on a thermal basis. So this is, again, this is a great addition to the Ansys tools, to anyone that's already using Maxwell or HFSS, and you're interested in thermal analysis. The workflow is very, very easy because you're already generating the data within, let's say, Maxwell. I can take a Maxwell solve and I can incorporate that EM data into my Icepak analysis by directly linking it. And so I'm saving time. I'm saving a lot of effort by having to reassign things, materials, closures, that sort of information. I can reincorporate meshes, so I'm saving time there. But again, the important thing is, at the end of the day, you're also getting that accuracy. And so that is what I think is probably, again, most impactful with these tools is you get the accuracy with Maxwell or HFSS, and now because it's using that CFD solver, you're getting the thermal accuracy for your tools using Icepak. So probably just the next, this is an overview of the packages offered. Again, since this is a kind of a high overview of everything, these are the tools. We've gone through basically all of them today. Probably in a little less detail for Maxwell with the difference between 3D, QD, and 3D, 2D, and QS. But here they all are. In some additions that are worth talking about is the Optometrics package. So that is a tool that you can incorporate into HFSS, Maxwell, Icepak, to do things such as parametric studies, design of experiments, optometric studies. If you're looking at mitigating or reducing or maximizing some value, an optometrics study is a great place to start and perform them. Included also statistical analysis. You also, if you include optometrics, that includes a distributive solve option, which is a way to increase the speed of your solves when you're doing a parametric or a optometric study. Of course, there is SpaceClaim as well, which is another tool that it takes in, for anyone that doesn't know it, it takes in geometry generated, let's say like a step file, for example, and it makes it so it is simulation ready. A lot of times when I'm taking in a step file from a client or a customer, there could be issues with the faces. There could be discontinuities. There could be missing or duplicated edges. There could be inexact edges. And this is a tool that you can use to refine the geometry so that it is simulation and Ansys simulation ready. And it really changed my workflow when introduced to it, because being a traditional FSS user, coming in, seeing if they're discovering that there is an issue with the geometry, increased the amount of time it took to get something simulated. And it can be, using those Boolean functions within HFSS, albeit they're great. It can be slow. And having a tool and having expertise using SpaceClaim allows you to refine your geometry before you bring it into these great simulation tools. I should probably also talk about HPCs, just in case there's any salespeople on the line, so that I can say that I talked about HPCs. No, of course, I'm kidding. HPCs, of course, allow the utilization of multiple cores. Traditionally, when you purchase a software such as HFSS or Maxwell or SI Wave, and this is most likely true for all of the other CFD and mechanical, you're able to use 4 physical cores while simulating, while the incorporation of an HPC allows for more cores to be used, and the first HPC pack allows the addition of 8 cores. So if I have HFSS and I purchase an HPC, I can now use 12 cores during my simulation, which, again, speeds up time significantly and is a great inclusion to the process while I'm using these simulation tools. And the nice thing about the HPCs now is they've moved and unified them at Ansys, so now they're all Ansys HPCs, is if I have an HPC, I can use it for HFSS, I can use it for Fluent, I can use it for mechanical, and it's all that HPC. So I can purchase one initially with the idea that I'm using it for HFSS, but as my workflows evolve and I need the inclusion of structural analysis or CFD analysis outside of Icepak, I can still use those HPCs to speed up now mechanical simulation, which is a great addition. I've got just a couple of extra slides for anyone that's got questions, but I purposely tried to leave myself about 10 minutes if there were any questions. Otherwise, that is what I have for today.